Okay, so we are recording. Hi everyone. So let me just. Okay, so let's start this seventh lecture. Okay, so last time we did. We started talking about the equation of a plane, right? In fact, we should say equations of a plane because they come in, I believe, at least in two different forms. So let us get that first. So, so we had a plane in 3D space. Of course, everything we do now is in 3D. So this plane, well, I mean, it's completely known if you know a point P on the plane and a normal vector to the plane, right? So if you know coordinates of a point P on your plane and a normal vector to the plane, the direction of this normal line at least, then the plane is completely specified, right? So, so last time I said that, okay, any other point in the plane can be specified by this equation, PQ is orthogonal to this normal vector n. So the idea is that any line that you draw in the plane is going to be orthogonal to this normal line n, right? So that's the idea. Okay, so and then this translates into this vector equation, or so this is equal to 0, or we can just say PQ in terms of dot product dot n is equal to 0. So, and this is the vector form of equation of the plane, right? So, vector form. So as we discussed the case of lines, we can write this equation in a kind of in coordinate form using XYZ coordinates, right? So that's what we can do. So now let Q be coordinates like generic point on the plane. Let's denote this its coordinate by XYZ. And this point also let P kind of original fixed points that we pick on the plane, x0, y0, z0, right? Then from these two, of course, we get that PQ, the vector, is x minus x0, y minus y0, and z minus z0, right? Okay, and now we are demanding that this vector PQ be orthogonal or orthogonal to this vector n. So of course, why don't we just give a coordinates for n? And if I write here, then you get yes. Let n as well be equal to ABC. So that's the tip, right? So maybe, yeah. Okay, so now we have everything that we need in order to write this in terms of Cartesian coordinates. So then this equation star gives us the following. PQ is x minus x0, y minus y0, z minus z0 is orthogonal to, dotted with ABC, is 0. But let's write this down. Let's see what this dot is here, right? So this dot now is going to be at A, x minus x0, plus B, y minus y0, plus C, z minus z0 is equal to 0. Okay, let's continue. So you get AX plus BY plus CZ. I just took the first terms. And then the constant is this term, AX0 minus BY0 minus CZ0 equal to 0. So we can call this whole thing to be D or minus D, doesn't matter. D is a constant, right? D is just a constant. Let's call this term, for example, D. Then the equation becomes this: AX plus BY plus CZ plus D is equal to 0. So this is the equation of a plane in Cartesian coordinates, right? So this is equation of a plane in, let me check, in Cartesian coordinates. Right? So this is, okay, so we have three equations now. This one in Cartesian coordinates and this one in vector form. They are completely equivalent. They are just two different ways of talking about the same thing. I mean, so when we write the equation in this form, we have to be aware that A, B, C, all three of them cannot be zero. Because if all three are zero, it means that, well, this vector is not really a vector, it's zero vector, and zero vector doesn't have a direction. So it doesn't specify the plane for me then, right? So what I have to do is to make sure that the vector is non-zero. So always in an equation of a plane, one of A, B, C has to be, I mean, non-zero. But what about D? Can D be zero, for example? Or should be non-zero? It can be zero. It can be zero. It's completely okay to be zero. And if t is zero, what happens? Or what does it signal about the plane if t is equal to zero? Mm-hmm.
It's on one axis?
No, it's close to that, but you're close. Next, yeah.
It contains the origin.
It contains the origin, exactly. So let us, yes, I have a good answer. Yeah, the origin is on the plane. Absolutely correct, yes, very good. So it's on the origin indeed. So let me write it here. So this was the equation of the plane, AX plus BY plus CZ plus D equal to 0. And then we notice that D can be 0 if and only if a plane passes through the origin. Okay, so that's very good. So let's do now a problem. Example rather. So let's find the equation of a plane that passes through 3 points. So example, find the equation of the plane passing through, am I on the line? Yes. I mean, within the boundary, yes. Passing through points P equal to 1, 1, 1, Q equal to 1, 0, 1, R equal to 0, 1, 2. So I hope we just gave 3 points, right? So we have these 3 points. And we want to find the equation of the plane that passes through these 3 points. We know that if 3 points are not collinear, if 3 points are not on the same line, then they define a unique plane, right? We know about that. If these 3 points are not collinear, they define a unique plane. And here I have made sure that they are not collinear. You should believe me. Okay, so how we proceed with solving this problem? This is not given the way that we were introduced the equation of the plane. This is given in different form. But how can we bring it to that form and then solve the problem? Yeah?
So the orthogonal vector to the plane is x, y, z, and
yeah, exactly. So what we can do is this. We can just choose two of these lines, maybe this and that. So let's take vectors. And to find the normal vector, we just take the cross product of these two. So n is QR plus QP. And then you're set, because then we can just choose this point Q, right? As the point that plane passes through, and then so let's try that. So what is QR? QR is R minus Q is equal to what is R? R is 0, 1, 2 minus 1, 0, 1. 1, 0, 1, yeah. No, R 0, 1, 2 minus Q, 1, 0, yeah, that's correct. That's equal to negative 1, and that's equal to 1, and we have minus 1. That's QR. What about QP? Okay, QP is equal to P minus Q. P is, we have it here, 1, 1, 1. Minus Q is here, 1, 0, 1. So let's find that out. Let's find that. So this is 0. And this one is 1. And this one is 0. Oh, there's a question. Yeah, so what's the question in the chat? Okay, maybe. The origin is on the plane. Find PQ and take the cross product. Okay, yes. Okay, I've got good answers. You can also talk. I mean, you can also unmute, as I said, and talk if you want. Because that, for me, that way is actually easier to follow you and to answer in more quickly. Okay, anyhow, so we have that. So let's take then the cross product. So that's equal to IJK. IJK, now we have, I said we have to form QR. QR is minus 1, 1, negative 1, and this one is 0, 1, 0. Okay, so now again, I have to be careful with these multiplications. So that's equal to I times, okay, this one is 0, that's negative, negative 1 becomes 1. Negative j times this one is 0, and this is also 0, so this is 0 plus k times negative 1. So we have I negative k. That's this vector n.
Should the z component for QR be positive 1, not negative 1?
Z component for QR.
For QR, yeah.
Or is it should be positive 1? R minus Q. R is 2. Yes. Thank you so much. Yeah, very good. Thank you. Excellent. So this should be then, I'm doing QR, so it should be 1 here, right? QR, it should be 1. Very good. And this is the 1. So I've got, this doesn't change, negative j. This is still 0 plus k times. Nothing changes though. That's good. So we've got I minus k. Okay. So now we have n and we have q. So the equation, so this is equal to ABC, right? So that's equal to 1, 0, negative 1. That's going to be ABC, which is n. So now all we have to do is just sub in into the equation. So the equation now is, what was the equation? The equation is a times x minus x0 plus b times y minus y0 plus c times z minus z0. That's also a form of equation that I immediately erase when I derived it, but we can use this form as well, right? So that's, so now A is, well, 1. Now x0, y0, z0, this is x0, y0, z0. I just chose this point. Okay, you get 1 times x minus, I mean, what was the coordinates of Q again? You have to tell me, please.
101.
Yes. 101. So this is 1, and then plus 0 times y minus y0, which I don't care, plus c, which is negative 1, z minus z0, z minus 1. So what do we get? We get x negative z plus 1 is equal to 0. Did you get this answer? Yeah, that's what I got. Oh, very good. Yes, that's what you got. Excellent. So, yes.
Sir, I was talking about n. Shouldn't it? I got -1, 0, -1.
For n?
Yeah.
Wait a minute. For n, you got -1, 0, 1?
No, -1, 0, -1.
Oh, -1, 0. Oh, that cannot be. Well, I mean, you may be right, but it doesn't match with this one. This is a different vector. I got this. I guess others also got that. Yeah.
I got -1, 0, -1 as well for the normal. Maybe I'm wrong, I'm not sure, but do you think you could go through calculating the normal again?
The normal is like this. I, j, k, and then we put this vector, so we have to agree what vector QR is. What is the vector QR that I derive? Isn't it -1, 1, 0?
The norm for I is incorrect. You have to redo I because you changed it to 1, not -1.
Sorry?
1 times 0 minus.
Oh, here is, oh, this is -1. Yes, yes, yes. Okay, very good. Okay, thank you guys. Yes, very good. That's -1. So are we all on the same page now? Okay, yeah, so yes, yeah, okay, so now I have one question about the equations. So you may get an equation of a plane of this form, ax plus by plus cz plus d equal to 0. And you may get another equation, a prime x plus b prime y plus c prime z plus d prime equal to 0. Can you tell me when these two things define the same equation? I mean, same plane? When these define the same plane? I mean, for example, your answer might be that they really define the same plane if and only if A is equal to A prime, B is equal to B prime, C is equal to C prime, D is equal. That's a possibility, but is it true? Yes. Yes, that's right. So the answer is that these two possibly different looking things define the same equation if and only if all these numbers is a multiple of the numbers in the second row. I mean, it's a scalar product of this with some scalar, right? In other words, A over A prime is equal to B over B prime, C over C prime is D over D prime. But you cannot write it like that because one of them may be 0. If one of them is 0, then that's not good. You just have to write one as a multiple of some non-zero constant with the other.
scalar is not the same, they're not the same.
If they're the same, then of course same equation, but that doesn't have to be like that. Question from the audience? I mean, the home audience? Okay, good. So now, one more thing I want to do is to define, to calculate the angle between two planes. So that's kind of nice result. Okay, so we've got here angle between two planes. Okay, so here's the situation. We have these two planes that intersect in one line. Imagine we have the two planes. And they form an angle like theta, right? So this is plane pi 1. This is plane pi 2. And so this is like your book. You have opened it like this with that angle theta, okay? So the question is, what is theta? So we want to find the angle between two planes. So these two planes come with, of course, normal vectors. This is given to us, imagine. So so this is N1 and N2 be normal vectors to pi 1 and pi 2. Okay, so there is this normal vector maybe coming off the board or something like that. So this is like N1, and the other one is coming in this direction, N2. And so the question is, can I just find this angle using N1 and N2? That's the thing. So if you think about it just like that, it's not very clear really what the angle would be and how to calculate it in terms of M1 and M2. But I can tell you this, look, I mean, if you have something like, so take these two lines. So imagine these are your two lines, and this is like theta. Then your normal is normal to this plane. I can draw it like that. And there is another normal line that comes normal to the other one, and this one. So this is the direction of this N1, and this is the direction of N2. So now, can you tell me what this angle theta is in terms of angles between N1 and N2?
180 minus.
Okay, any other guesses, answers? Because if I know this angle theta in terms of angles between these two vectors, N1 and N2, then we can use that formula that we had for angles between two vectors, you know, from first lecture, second lecture. Then we can compute everything. Right? So that's it. But how can, what's the relation between this angle theta and this angle? Audience, yes. Yes, I got the correct answer also from the audience, and correct answer here. Yes, indeed, if I call this theta prime, I claim that theta prime is equal to pi minus theta. And you have to ask me why. Theta prime is equal to this one. Why? Because in this quadrangle like this, right? So this is 90 degrees, this is 90 degrees. The total sum of the angles is 360. These are 180, so remains 180, which is sum of these two. I mean, theta plus theta prime plus pi over 2 plus pi over 2 has to be equal to 2 pi. Sum of angles is 2 pi, I mean, for this quadrangles. So this tells me that then theta plus theta prime, it should be equal to pi. Okay, so this is exactly this relation that some of you mentioned, right? So that's what we need. Now, okay, so if I know this angle, I know that angle, but the situation is even a bit easier. What is the relation between cosine of these two angles? Because eventually we are going to compute cosine first, right? So can we just compute the cosine first of this theta? We have two angles that add up to 180 degrees. What's the relation between their cosines? That's the question, right?
1 minus cosine theta 1 square equals.
It's simpler than that. If two angles add up to pi, 180, cosine of 1 is equal to what? For sine, that's correct. Minus cosine of the other, yeah. So from here, you immediately get that. So this is a bit of trigonometry exercise. Cosine of theta prime is equal to minus cosine of theta. So of course, then it follows that absolute value of cosine of theta prime is equal to absolute value of cosine of theta. And to see this, just remember what is cosine, right? If you draw, I know you are more comfortable with drawing triangles, but let us draw this circle. So this is theta, and this would be theta prime. And so this is, this is theta prime, but this is theta prime, indeed, sorry. This is theta prime, right? Because you subtract here same amount, the remainder is theta prime. Okay, so now you want to compute cosines, right? Here you have to draw and compute this. Draw this perpendicular and compute. You see that this is cosine of theta, but here you go to negative for sure, right? So this is negative cosine of theta, which is cosine of theta prime. Okay, so then the end result is that absolute value of cosine of theta prime that we can compute easily is absolute value of cosine of theta. Okay, so then what we need is this now. So absolute value of cosine of theta is equal to n dot n prime over a normal band. From formulas for the dot product, you remember, right? From, I believe, dot product lecture. Let me see if there are questions. No. Yes?
When you're saying n and n prime, is that what you mean by like n?
Oh, n1 and n2, I'm sorry. Yes. I was carried away by this prime business, so this is, thank you. Okay, very good. So from dot product, formula. Of course, this is. Okay. So that's the formula you can use. Now you have to be careful about the magnitude, but because it could be positive or negative, so that needs a little bit of more care. But so far, I think that's good. Okay, so that's one thing. Now another thing I want to do. So we covered the angles. Okay, so yes. So, oh yeah, the distance from a point to a plane also is a good topic to discuss. Any questions about the angle computation? For example, if you agree that you're always computing the kind of angle between 0 and pi over 2, then you can just drop this. You're computing the angle. I mean, you can have, the two planes. One of the angles is bigger than pi over 2. The other one is less than pi over 2. So if you want to compute the one that's less than pi over 2, you don't even have to do this. You can just, anyhow. So any comments or questions? Okay, so there is a comment in chat. Can you use cross products to do the same? Cross products to compute the angles between two vectors. I suppose, can we use cross product to compute angles between two vectors? What was the formula? Was length of this, length of that, times sine of theta, right? So yes, we can do that, yeah. Yeah. But doing dot is easier than cross. I think even I can see that, yeah. Yeah. Okay, so that's, right, so let's erase that. Now we need to compute distance from a point to a plane. So distance from point to plane. So again, we have our plane, phi, there is this point P, and we want to compute the distance. So we have a kind of intuitive idea of what distance is, right? So the distance is we drop a perpendicular line to the plane, and then we just compute the length of this vector, right? So this is the one, and then so this is orthogonal, for example, and this D is the distance, and the question is what is D? Okay, so how can we approach this question now? So let's take a point like Q on the plane, right? And then this line, so let's call this P prime. This line is also orthogonal. I mean, for all points in the plane, Q in the plane, this line QP prime is orthogonal to this line, right? So this is also 90, right? So then we have this QP vector. And what we are doing, we are projecting this QP vector on this line, and we want to compute this one, right? This line. Okay, so how we should proceed now? Can you tell me what formula we have to use and stuff like that? Yes.
Would you need to project QP onto the normal?
Yes, exactly. We just project it onto the normal. So imagine you have chosen your, so this is like a normal line, right? D. So the formula then is going to be D is equal to length of, absolute value of PQ. So this is Q. This is my Q now. Yes. So PQ PQ dot n divided by n. So we can write that now using the formula for dot product. This is length of PQ, right? This is norm of n, norm of PQ times cosine of theta over d. So basically, so I went from here to there. Yes, that's the way I wrote it in my notes. I'm not sure that's the best way to put it. But the formula is this anyhow. The final formula is this. So I can even question this.
Wouldn't the magnitude of n be squared if we're doing projection?
The magnitude of n, but I have n here also. I don't think so. So let me. No, I mean I have just no actually. But the formula that we are using for magnitude of n, remember, I think was a bit different compared to this situation. I think we have to use.
N is normal vector.
N is normal vector to the plane. Yes. N is normal vector to the plane. Yes. Okay. So, but this is not the best formula that you can get. The best formula that you can get is the following. So from here, so assuming the coordinate of P equation of the plane is, so let's give an equation to this plane. This would be ax by cz plus d equal to 0, right? So ax plus by plus cz plus d equal to 0. And let's assume P has coordinates x0, y0, z0, right? And that P be equal to x0, y0, z0. So let's take this point Q. So I said Q is a kind of generic point on the plane. We can just choose any point on the plane, right? We can just choose any point that we wish to be on the plane. So let's just Q be equal to x, y, z, any point on the plane, as we are allowed to do it according to this formula, right? Any point on the plane. Okay. So all we have to do, we have to sub into this formula and then compute. That's all we have to do. So what happens? Then PQ, of course, is equal to Q minus P. So this vector is Q minus P. So that's equal to x minus x0, y minus y0, and z minus z0. And the normal vector n, of course, is ABC, which is this one. Good. So this is ABC. So we can just sub in. Now we are ready to sub in. So let's compute, first of all, PQ.n. So what is that? That's equal to x minus x0, y minus y0, z minus z0, dot ABC, dot ABC. So let's compute that. And this is equal to, so I'm going to erase this part. So that's equal to, let's just spell this out. This is equal to a times x minus x0 plus b times y minus y0 plus c times z minus z0. So that's equal to ax plus by plus cz minus ax0 minus by0 minus cz0. Okay, now how can I simplify this further? Because I got a monster here, right? X, Y, Z, I don't know what they are. I just chose a point on the plane, but I don't know what point I chose. So it's not advisable to say that, okay, go and pick an explicit point on the plane and then sub into this formula. That's not a good idea. So I've got that and that. How can I simplify this now?
The AX naught minus BY naught minus CZ naught, you could just make it B.
Absolutely correct, except that we have to put X, Y, Z, because I chose X naught, Y naught, Z naught to be out of the plane. So that's not, so X, Y, Z is on the plane. I just chose it like that, right? So, but here is the equation. And I said that any point on the plane here, right? Okay, so this is then is equal to, can you tell me what this number is? Well, we have it here. Minus d, yeah, that's minus d. So that's equal to negative d, negative ax0, negative dy0, negative cz0. So, okay, then d, oh, this is not very good. So the distance d, I'm going to change distance, not to confuse with that little d over there. Distance d, cap d, is equal to absolute value of that, but so this is, absolute value of negative is the same, so this is equal to absolute, let me put it like this. Let me not go too fast. Okay, so is over square root of a2 plus b2 plus c2. Now, I can simplify this at least to look a bit better. It's completely equivalent, but let's write it as absolute ax0, by0, z0 plus cz0 plus d over square root of a2 plus b2 plus c2. That's very. This is a kind of more practical formula for finding the distance between a plane and the point out of the plane. So remember, the situation was like this. This was a plane, right? And this was this point P, which has coordinate x0, y0, z0, and we drop this line and we call this distance d. That's the formula. Any questions or comments about this? Okay, so it seems we have covered good ground here. Now we can just move into this section where we discuss quadric surfaces. So that's another interesting thing. Can I erase this part now? Okay, there are no questions. Good. So let me erase then everything. So now, quadric surfaces. So our goal now is this. We want to understand what kind of shape a second degree equation basically specifies in space, right? So the goal is to understand what shape. By shape, I really mean a surface, for example. Surface corresponds to a second degree equation in x, y, z. What do we mean by second degree equation? We really mean something that's quadratic in x, y, z. But it could be, for example, xy is also second degree because it's degree 1 in x, degree 1 in y, so xy is second degree general. So the general form is of such equation is this. We've got ax squared plus by squared plus cz squared plus abc dxy plus exz plus efyz plus, okay, so these are, we have taken care of all second degree terms. Now we allow first degree terms also because it can come into the equation, right? Plus g, x, e, f, g, h, y, I, z, plus, what is the next letter in the alphabet? A, B, C, D, F, G, H, I, J, K, yes. K equal to 0.
J comes after that.
What's that? Oh, J. You see, because this is not my original language, I have to start from beginning each time I put it in.
Me too. That makes you feel better.
Really?
Yeah,
I do.
me too.
No, but you learn, this is your mother tongue.
No,
so.
but you asked me like one comes after I did it all and I have really.
Is that right? No, but this is, well, actually my own original language, I don't know how to. Completely forgotten everything. So, but not forgotten, but then I have to think. So, because there are like 32 letters there, so that's even 4 more. So, okay, so we have this equation. Ax squared by squared. If 32, I'm not sure 100% really. X squared by squared cz squared. So this is the general form. Now, this is a tall order. Okay, so this is very difficult to handle in general. If you, for example, if there are, so these are like cross terms, right? Cross terms. So this is way too difficult in a way for us now. Of course, I mean, you know, you have learned in linear algebra enough techniques, I believe, to be able to handle this equation. If you just take next step in your linear algebra, then you can handle this sort of questions. But in general, it's more complicated than what's expected in this course. So let me put it like this. I wouldn't say too difficult, but it's difficult to handle the general case. But what we do in this section, in this book, is that we consider some cases, sub-cases, and we tell you exactly what figures correspond to those. And then you have some good supply of these cases. And so there's going to be about, I think, 8 cases or something. Okay, so the easiest case, but the time is up anyhow. So we pick up from, I think, from Friday, the rest of the issue. So in general, I think we're going to start with spheres, with ellipsoids, with hyperboloids, and with Again, it's hyperboloid of one sheet, hyperboloid of two sheet, parabolic ellipsoid. Oh, there are all kinds of things. So it's going to be very confusing, and you have to remember. There is some logic in this terminology, so you have to remember. From Kevin Grogan, is it a cylinder? In general, it's not a cylinder, no. I mean, in general, could be an ellipsoid. For example, could be an oval. I mean, not oval. You know what is the three-dimensional version of oval? But there is a term also for oval. Isn't it ovaloids or something? Ovaloids? I think there is. Huh? Oval is essentially like egg. But I was talking about ovaloids. What is that? Well, you check on Wiki, that's okay.
Like a grain of rice.
Grain of rice, yeah. Yeah, that's right. So I mean, I'm not 100%, but we call it actually, we don't call it this, we call it ellipsoid. As you said, I mean, you said ellipsoid. Okay, guys, thank you so much. I just stopped the recording and then